Okay, before I forget, on your assignment sheet going right in next class, we're going to have a quiz over limits that we've learned thus far. We gotta have a quiz somewhere. So we'll do it now while stuff's still easy. So next class we'll have a quiz over the limits that we've learned so far, including today's assignment. Alright, so taking a look at what we have so far up here for warm-up. What did we get for number 1? 4. Do you agree? Okay, any questions on that? Straight substitution for that guy. How to use your noggin with your logs, right? Alright, number 3, what did we get for answer? Whoa. Negative 110? Okay. What did we end up having to do with this guy? Let's just figure it out. Good, we had to factor and take out negative. So on top we had to take out a negative, so we had the limit as x approaches 5. Negative, this becomes minus 5, this becomes plus x, so that is minus 5. And in the denominator, we had x minus 5x plus 5. So then we had our minus 5, so reduce. And when you substitute, don't lose that negative. That's awesome. Good. Number 2, what did we get for this one? Alright, and number 4, what did we end up getting? I heard 0, and then I heard murmurs. 116? Should we take a look at this? Negative 116? What do we have to do for number 4? Yeah, we want to get denominators the same, right? I want a single fraction on top. And our bottom, it's already combined, it's just one single term there. So I need to get one single fraction on top so we can then multiply by that reciprocal. So on top, I'm going to need to multiply by x plus 4 over there and times 4 over there. All right. Oh, this is the part I always get to, and then I remember I actually made myself space over here. Okay. So I have at the limit as x approaches 0. So 1 over x plus 4. I needed to multiply this guy by, and over here, minus 1, 4. I needed to multiply by x plus 4 over x plus 4. Alright, and then in our denominator, we're still doing that x. Alright, so combining, multiplying, all that jazz. Up top, we get 4. Now you gotta be careful because that's a negative 1 that's getting distributed there. So minus x minus 4. Do we agree with that? And that's all over our denominator 4 times x plus 4. And since we're in here, let's just go and multiply by that reciprocal. So I'm going to multiply by, instead of x, 1 over x. Alright, what do we have happen here? Good, the 4 is reduced. Our x is reduced. Make sure you don't lose this negative though. So we end up, this is the limit as x approaches 0. Negative 1 over 4 times x plus 4. And now when we substitute in, ooh, that 0 is looking a little crazy. Now when we substitute in our 0, we get negative 160. Okay, now then I just negative 160. Questions on that one? Once you actually substitute it in. So the limit means that we are considering what's happening as we approach that value. So once we're able to do that direct substitution, or we already know the limit, like the limit of x over sine x, then we can drop that limit. Other questions? Okay. And then number 5, the piecewise. I don't know if we did a piecewise like this yet, so I want to make sure we touch base on it. So it says find the limit of g of x, the limit as x approaches 1 of g of x, where g of x is this piecewise function. Now, when we look at the point we're talking about, that ends up being the point where the graphs are broken up. So we need to know if these points, or these two graphs meet up nicely, or if they end up being broken up. Because if they meet up nicely and they're approaching the same value, then we have the limit exists. But if they're in different spots, we have that jump, the limit's not going to exist. So anytime we have that piecewise function, we need to investigate the left-hand limit and the right-hand limit. Alright, so I need to first check out limit as x approaches 1 from the left of g of x. And let's go and talk. Let's go and put in which function that is. So 2x minus 1, because we need to know which piece you're using. And so if we go ahead and do our direct substitution here, when I put 1 in, we get 1. Right? So that's my left hand limit. Now we need to also check the right hand limit. Because in order for the limit to exist, they need to be the same value. Alright, and so from the right hand side, because x is greater than or equal to 1, we use this bottom function. So we have x squared minus 3. When I take 1 and substitute in there, we get negative 2. My limits do not meet up, so we can say, therefore, the limit as x approaches 1 from the left of g of x does not equal the limit as x approaches 1 from the right of g of x. Therefore, the limit as x approaches 1, that overall limit of g of x, does not exist. So in calculus, you'll find that they love to make you explain why or justify that. Now here, it simply said define the limit, so I would expect to see your work here, and then you can go and make that. But if it asks you to justify or show your work or something like that, explain why, you would need this additional step that they cannot equal. It's good to go get in the practice of that now, because that's almost always going to be asked of you. But you would need to show your work and then state that does not exist. Now, if they asked us to find the limit as x approaches 2, what would we do? Yeah, 2 means that we would use this bottom piece, because 2 is greater than or equal to 1, so we just substitute it and we're good to go. So just because it's a piecewise doesn't mean it's immediately going to blow up. It's just when it's a piecewise where we're investigating the point in question, then you've got to investigate that left. Questions on that? And then number 6, what did we get? Who wants to volunteer for the gap? What do we have to do with this guy? We could try separating. So we know from our notes last class, I think it was last class, that we have the limit as x approaches 0 of x over sine x, or we could flip-flop that, or the limit as x approaches 0 of 1 minus cosine x over x, or cosine x minus 1 over x. But the issue here is that we don't have the x that's necessary for that, right? We could try multiplying by something here, but there's something else that we could actually do. Close. It's not double angle, but just, it's a trig substitution. You're right. Let's think back to our just regular Pythagorean identity. Sine squared plus cosine squared equals 1. Couldn't we substitute something in for sine squared here? So we can do a trig substitution with this. Alright, so when we do that, let's change numbers. Get the limit as x approaches 0. 1 minus cosine x we leave alone. Now in our denominator, so sine squared ends up being 1 minus cosine squared. What can I do from here? Yeah, we can factor the denominator here. We cannot right now just reduce cosine x into cosine squared x. That's a huge algebra issue there in multiple ways. But we can factor our denominator. So this would then be the limit as x approaches 0 of 1 minus cosine x over 1 minus cosine x, 1 plus cosine x. Then we've got our factors here. Reduce. And now if we try direct substitution, we get 1 over 1 plus cosine of 0. What is cosine of 0? 1. So what do we actually get for answer? 1. Now we probably could have gone ahead and multiplied by x over x to help us out with getting that into where we can use those trig values, or those trig limits that we do know, this is probably the easier, quicker way. All right, any questions on those limits? Okay, let's go take a look at questions. Now I know there are two chunks there. So I guess we'll just start off. Any questions on that first page? And did we have any questions on our second page? 20 and 23. The limit is x squared just 1 with cosine of pi over 2x. Is that the right one?
No, it's
this guy. Okay. So for number 20 here, when we multiply by the conjugate, the key thing is that we end up with 9 minus x on top. So we had to factor out a negative for that to match up with my factor denominator. So when we factor out that negative, then we get where we have x minus 9 both on top and bottom. Those reduce, and we're left with the limit of 1 over 3 plus root x. Then when you substitute, you're still good. So you end up having to pull out that negative. With number 23, so conjugates, still some ideas, but remember, guys, that for conjugates, we only change the sign in between the radical and our other term, okay? You don't change the sign underneath your radical, it just puts it in between your radical and other term. So when we factor that one out, we end up getting, in the denominator, it's simplified down to x minus 14. So your x minus 14 should have reduced there, and left you with just that square root of x minus 5 plus 3. So we end up getting, this is x minus 5, those cancel, and then minus 9. So x minus 5 minus 9, which gave us the x minus 14. See where we went wrong with that? Other questions on either page? What?
Yeah.
Number 17?
Yeah.
This guy with the factoring craziness. So we had to do with our sum of cubes. Our top one multiplies to 12, adds to 7, so we had 3 and 4 for that. Now our sum of cubes, so we had x and 3 were our terms we were working with. So same sign, opposite sign, always positive. So x plus 3 and x squared minus 3x plus 9. So you should have had your x plus 3's reduced. Now, in a sum of cubes, you can't factor that last chunk. So when we get to our remaining part, where it's the limit as x squared is negative 3 of x plus 4 over the x squared minus x plus 9, when we do direct substitution there, careful with all of your negatives. You should have gotten 1 on top, and then the denominator you would have gotten 9 plus 9 plus 9. So if you got a minus 9 there's something, probably a positive negative. Other questions? Now again, keep in mind, I know the key might be a little different sometimes because another teacher did this key, but for here, for us, when we have it's going to infinity or negative infinity, I do want you to write D and E parentheses which one it's going to. Don't just write infinity or negative things. I want to keep doing that concept that it does not exist, but we're interested in where it's going. Other questions? Yes.
Kind of semi-unrelated. On one of them, are you able to, for sometimes when you get any like fluid in and out, and then freeze what the else would be, would you imagine that? Around 15 on the second. I just like jump out.
Hold on. Is this the page you're talking about?
Yeah. We got we get the negative 1 times or 1 times.
So L'Hopital you use when you get that indeterminate form of 0 over 0 or infinity over infinity. Here, we don't get that, we get 5 over 0, so you can't use L'Hopital on this.
So only 0 there or
Yeah. Good question. In general, I believe the answer is that L'Hopital should give you the same answer as another way. Come again. Yes.
So for 19, we have to test the negative on the top and the positive on the top.
Yeah, so because it's not asking for specifically from one side, I think our notes was asking only from one side. So we need to check both the left hand and the right hand. That's what's happening. Yes. 17 right here. So here we're checking from the left. So we remember we've got a couple of options. You can think of your graph, or you can do it this algebraic way. So this is that broken up graph. This is what our broken up graph normally looks like, but it's been shifted to the right side. So it would be that same idea, just over here. So approaching 7 on the left, if you think of your graph, that's going to be -1. Or taking it from the algebraic form, since we're approaching that vertex, it's not really a vertex, but the vertex from the left-hand side, then that means we want to take opposite of the computer. So we have the limit as x approaches 7 from the left is the same thing as taking out that negative. Or not taking out the negative, it's considering the negative version of that absolute value. So it's using that piecewise definition for the absolute value. The absolute value of x minus 7 is defined as opposite of x minus 7 on the left side and just x minus 7 on the right side. So since we're approaching that left side of the vertex, then we would be doing the opposite of that. So then when we reduce these, at least we've got -1. So either way, whichever works for you. Go ahead.
Why is the negative one so for x?
This one here? 19. So when we consider the left-hand side, we end up having those reduced, but we're left with that -1. So again, it's that left. Yeah, so the left-hand side is that negative version.
So number 17, if it was coming from the right, we could just do it regular.
Yeah. So if it was coming from the right, thinking of your graph, it would just be that positive one. But doing it algebraically, because we're coming from the right-hand side of that vertex, it would just be x minus 7 over x minus 7, which gives you that positive. Other questions? Good questions. Yeah. 32. 32. This guy here, the sign up. Okay. So just direct substitution here. They always get you throwing 1 at the end, right? If we just substitute in 0, then we can do sine of pi, which is 0 over pi, so we don't have an issue. Other questions? Okay. So today we're going to be taking a look at limits at infinity, which we've already talked about. And really, this you did in Algebra 2 and you did again in pre-calc. So it's going to be that balanced, top-heavy, bottom-heavy, horizontal asymptote stuff with a little bit more to it. But we'll do that, and we'll just touch our toes into the continuity water today. So we'll do more continuity stuff. So if we come from the right hand side, so -2 means we want the -1.9. Minus negative would give you that positive overall.
So wait, if we're going from the right, we want more to the left.
So because we're coming to -2, so if you think of that number line here, from the right hand side, we would want like -1.9.
So if we're going from the right, we want one just right.
Yeah, we want something just slightly to the right, which, and then negatives seems like a smaller number. Another one. There's too many guesses.
Does that make sense?
Yeah.
Is there anyone that did not get the notes? Alright, you guys see that there are words on this page, right? And nothing on that page, right? Alright, I want you to read the top while I deal with my technical difficulties. Just want to make sure I wasn't crazy here. That was magenta for you.
I think it's just knowing what's out.
Never. We go to the whiteboard.
Yeah, you're WAP.
Nothing stops us from doing math in here. Is it too much to ask for a normal weight screen? Okay. You guys see what I see, right? We see notes now. Great. All right. So limits at infinity. Again, we've already kind of talked about this, but we looked at it more so with graphs. Not so much algebraically. Today's kind of looking at it algebraically. Now, limits at infinity really comes from the horizontal asymptote. In fact, the horizontal asymptote is defined as if my left end behavior, or the limit as x approaches infinity, approaches a single value, then that's the horizontal asymptote. And if my right end behavior, or the limit as x approaches infinity, approaches a single value, then that's also a horizontal asymptote. So either one needs to happen in order for there to be horizontal asymptote, which means we can have at most two horizontal asymptotes. We can have a different one on the left than on the right. And we'll investigate that today. So remember, horizontal asymptotes tells us what's happening at the ends of our graphs. It's okay if the crazy stuff happens in the middle. So in the middle of your graph, you might cross that horizontal asymptote. That's fine. Because the horizontal asymptote tells us about the ends. Now remember, vertical asymptote, we should never be crossing. There's a huge mathematical error with that. The horizontal asymptote just tells us what's happening at the ends. All right, so you might hear me refer to this as left end behavior, right end behavior, but it's the same behavior. All right, now we have our three cases that we learned back in Algebra 2. Bottom heavy, I don't like even. I feel like it makes it sound like the degrees have to be even. Let's call it balanced. So bottom heavy, balanced, or top heavy. And these were the three scenarios that you learned about in Algebra 2, and then you did it again in pre-calc. Now, depending on what Algebra 2 you took, you might have just glossed over top heavy, or you might have actually delved into the world of slant asymptotes. But the key thing with top heavy is that there is no horizontal asymptote. We instead have a slant asymptote. So with that, instead of having a horizontal asymptote where it approaches a single value, we have that our ends are going to be going either to infinity or negative infinity. So we'll have to do a little more investigating to decide if it's a DNE positive infinity or a DNE negative infinity. Now, bottom heavy and balanced are very simple. Bottom heavy, if our degree is larger than the denominator, the bottom has more degree than the top, then the limit is 0. So the horizontal asymptote is y equals 0, which means our end behavior is 0. And then balance, so if the degrees are the same, both on top and the bottom, that the largest degree at top is the same as the largest degree at the bottom, then we have a horizontal asymptote at just taking the ratio of our coefficients. So for a simple example for this, if we had, let's say f of x was 2x squared minus 3x over 4x squared, then our horizontal asymptote here be y equal to 2 over 4 or 1/2. So then that's going to be my end behavior, regardless of whether I'm going to the left or to the right. My horizontal asymptote is going to be the same. So bottom heavy, immediately our end behavior is 0. Balance is going to be those leading coefficients. Top heavy, then it's going to be either positive or negative. Now, again, we'll take a look on the back-hand side at what it looks like when we have two different horizontal asymptotes. Okay. Now, something I want to add to this. So we have our properties of limits that we learned where we had the constant rule, the identity rule, we had the sum and difference, the product, the division, as long as those limits existed. Now, those properties also apply to limits at infinity. So I want to go ahead and just run in a little extra blurb in this space here. So it's going to write if the limit as x approaches infinity, and we'll just go ahead and combine it together, we'll say positive or negative infinity. Really, we should write it twice, but save yourselves in there. So if the limit as x approaches positive or negative infinity of f of x, and same for g of x, and the limit as x approaches negative or positive infinity of g of x exist, so this is really starting off the same as our other properties, except before our property said the limit as x approaches c, or a single numerical value. So here we're saying the limit as x approaches positive or negative infinity. So if those both exist, then the sum and difference rule hold true. Our product rule still holds true. Our quotient, our quotient one, I'm trying to think about all we have. We still have the power rule holds true, so thus with that, we would have that product rule holds true. We can take the squared outside the whole thing. And then the other one's called your constant multiple, which is really just that coefficient. So we'll work it out. Constant multiple, which is just that coefficient. That's where we said if we have the limit as x approaches infinity of c times f of x, we can take that coefficient out. So as long as our end behavior limits towards infinity exist, meaning they approach a single numerical value, then all of these rules still hold true, or properties still hold true. Alright, so for example, with number 6, we could go ahead and say the limit of the first minus the limit of the second. We can use that property of the sum and difference. Likewise, with number 7, we could say the limit of the first, you could take those coefficients out in front, the limit of the second, which is just a constant, the limit of the third. So basically what it says is we can still apply those same properties that we applied before. Alright, questions with that? So type 1, if it's bottom heavy, remember our horizontal asymptote is y equals 0. So that should be our end behavior. So number 1, the limit as x approaches infinity of 2x squared plus 1 over 3x cubed minus 7. So we are interested in only the largest term. Because when we think about putting in infinity, you can't really plug in infinity because it's not a number that you can attain. But if we put in a super large number, this plus 1 is going to become insignificant compared to what's happening here. And the minus 7x is going to become insignificant as well. So really, in the numerator, the 2x squared holds the power. It determines what's happening. And in the denominator, the 3x cubed also holds the power. The denominator determines what's happening there. So we really just compare our largest terms. And if we look here, we see the term in the denominator has the large degree. So this is one of our bottom heavy cases. So the limit as x approaches infinity is just 0. As long as they are bottom heavy. And again, it's going to be the same if we had it approaching negative infinity. Your horizontal asymptote is the same on either side with our bottom heavy ones, so it's still going to be 0. So what do you think number 3 is going to be? 0. Now number 4, we throw in a sign. We say, what? We never did that before. How can we do this? So again, let's think about this. Now, we see we have an x squared in the denominator, and so we know that's going to be growing pretty fast, but we need to see how does our numerator impact us, because that's not a polynomial. Well, think about your graph of 4 sine x. What is the largest value that can possibly be? 4. What's the smallest value that can possibly be? -4. So, whereas up here with number 2 and number 1, the top would keep growing and growing and growing. Well, down here with number 4, the largest it could possibly be is 4 on top, and the smallest it possibly is -4. That's going to be insignificant compared to the denominator. So if I think of this fraction as a whole, which is growing quicker, the top or the bottom? The bottom for sure. So we're again going to have, if my denominator increases larger than the rest of it, then that would be essentially as 1 over infinity. And what does that whole thing approach say? 0. And that's what the idea is happening with each of these. Again, the denominator up here for number 1 is growing faster than the top. And so as we get to very, very, very large numbers, it's going to be like it's approaching 0. Or it's going to be kind of like 1 over infinity, or a small number over a huge number, which is close to 0. Does that make sense for number 4? Do we have questions on that? So when we throw in trig, you've got to stop and think a little more. All right, I want you guys to try 5 through 9. Again, remember with numbers like 6 and 7 that you can apply those properties. So like number 6, you should take the lead first. So you could have, but instead of doing that, so the limit of the first, that's the second. So the limit of the first is 0, but what's the limit of the second? All right, what do we get for number 5? 0, good. Now number 6, what do we get? Good, -7. So again, applying those properties, we can take the limit of the first, which we know to be 0, minus the limit of the second, and the limit of any constant is just that constant, so 0 to 7, which is -7. What you could have done instead of using those properties is actually gotten these together as one fraction, in which case you would have had the limit as x approaches infinity of 1 over x minus, how about an x? 1 over x minus 7, we would have had to multiply 7. We would have had to multiply that 7 times x over x, and then we would have gotten the limit as x approaches infinity of, let's see, 1 minus 7x over x. And then here we end up having that case, the balanced case, which we'll talk about on the backside, where degrees are the same. So our, if we go up here, our horizontal asymptote, or the end behavior, ends up being just the coefficients there. So we would have had -7 over 1, which is the -7. So either way, but as you can see, applying the properties allows us to avoid the algebra. All right, number 7, again, we could have combined all of that together or just done the limit of each individual one. What do we get for number 7? 9, good. Here we have bottom heavy, so it's 0. Constant, so 9. And bottom heavy, so -0, so the answer is 3. All right, questions on that? Okay. Now, number 8, we're entering into different territory. This was not bottom heavy. We end up having that it is balanced, or essentially the top and the bottom, the x's are growing at the same rate, so we take just our coefficients. And since we have balance, the degrees are the same. Our coefficients end up being 4 over 1. So just, and then number 9, what was our answer? 0. Questions on any of those ones? so here we have our balanced case. Again, I don't want to call it even balanced. Where essentially our largest term on top and largest from the bottom, the x's are growing at the same rate, so we compare coefficients. So number 10, x squared trumps the top, 3x squared trumps the bottom. Same degree, so our limit is just going to be those coefficients of 1 over 3. Alright, so I want you to go and try 11 through 15, and again, to be mindful of number 13 with that sign. Yes, John.
So on the AP exam, does, like, do they want, have they ever asked, like, to solve these, like, algebraically, or?
No, honestly, they probably wouldn't ask a limit this easy on the AP exam. They would probably give you something a little more complicated. If they were to give you one like this, it'd probably be a multiple choice, in which case you can use whatever method to get to your answer. Yes.
So the 67 balance.
Yeah, so when you end up combining these together, if you write this fraction, it you need balance. Because we can apply the properties we have it on there.
If you manipulate algebraically, you can expect it to balance. If you just use the properties where you can take the limit across each one, then it's but just so don't ask me. Maybe just Alright, let's go take a look at these. It sounds like we've made good progress with these. Alright, what do we get for number 11? Negative 4/3. Alright. Number 12. Negative 1. Good. So you got to be careful. It's not always going to be in proper standard form. So we had our largest term on top was negative 2x cubed. Our largest denominator was positive 2x cubed. So negative 2 over 2, which gives us negative 1. All right, now number 13. Again, we have that sneaky sign come back in. So here it's a little different. We know our largest term in the denominator is at 7x to the 4th. But up top, we need to figure out what's taking control. Now, for sine x, again, the largest it could be is 4. The smallest it could be is negative 4. So when we're plugging in really large negative numbers, like negative 1,000,000, this again becomes insignificant in comparison to the negative x to the 4th. That negative x to the 4th is going to really take over the whole numerator. So this becomes insignificant, and my negative x to the 4th is what holds the power. It's what controls that numerator. So we're comparing now that negative x to the 4th to 7x to the 4th. Again, we have that balanced. So what is my overall, or what's my limit going to be as x first? Okay, negative 1. Yes.
Is there ever going to be an instance with the other way around and sine taking control of something?
Probably not with the types of problems we'll be, at least consider that. Most likely the ones we'll be giving you, they're probably going to be insignificant. Good question. All right, number 14 would begin. Yeah, that wasn't very exciting. And then number 15? Yeah, yeah. All right, so again, the idea here is that my x's are growing at essentially the same rate, if you would. So we look at the coefficients out there. Now, technically what you do for this algebraically is that you divide each term by what's within there, but if you remember your balanced top heavy and bottom heavy rules, you can save yourself a lot of time. All right, so now let's talk about top heavy. Again, top heavy, that's where we have that slant asymptote. So we know it's not going to have a horizontal asymptote, thus our end behavior is going to be some form of D&E. But we need to know, is it D&E towards positive infinity or D&E towards negative infinity? If you dealt with slant asymptotes, you might have sometimes seen the graph. It might have looked something like this. Let's see. Let's say that was my vertical asymptote, and if this was my slant, it would have looked something funny like this. That's just one version of what the slant asymptote or the top heavy might look like. So as you can see, as we approach positive infinity, this is shooting up towards positive infinity. And here as I go to negative infinity, my graph is shooting down to negative infinity. Now that's not always the case that negative infinity indicates negative infinity. I could have had it flip-flopped the other way. But we can see that it's not approaching one single value because there's no horizontal asymptote that it comes back to. It's shooting off to either top infinity or negative infinity. So we have to investigate that. All right. Now with top heavy, we've got a couple of ways we can do this. Let me get this out of the way. Have you guys heard of the end behavior models? Got one yes and then some questionable maybes. Okay, so end behavior model basically tells us, well, what the ends of the graph is going to look like. And so we technically have been using kind of an end behavior model all along. If we look back at my balanced here, what we're saying is that, for example, number 11, this crazy rational function, the ends are going to match what the ends do of my function just negative 4x to the 7 over 3x to the 7. Or in other words, negative 4/3. So my ends are going to be matching just the line negative 4/3, which means they're approaching that negative 4/3. Likewise with my bottom heavy. Let's go with number 9 here. My end behavior model here would be that this crazy rational function, the ends are behaving or doing the same thing as the ends of the graph, 10x cubed over x to the 4th, which ends up simplifying down to 10 over x, which we know the ends of those graphs, you think of just your basic rational function, the ends of that graph are approaching 0. So the end behavior model basically says that if you take that largest term in both the numerator and the denominator and simplify that, that's going to be what the ends look like on a similar graph. So for number 1, my ends would be similar to 2 over 3x. Number 5, or number 6, no, that's not together, let's take another one. Number 3 here, my ends would be similar to the graph of 1 over x squared. Number 14 here, my ends would be similar to the graph of negative 4 over 3. So slant asymptotes, the top heavy ones, sometimes the end behavior is easier to think of rather than plugging in numbers. That's your other option, is to just simply plug in a very large positive value or a very large negative value. So top heavy, I feel the easiest method is to consider your end behavior models. So let's back up and consider. End behavior models. You might see me abbreviate that as EBM. And again, all that simply is taking your largest value in the numerator and your largest term in the denominator, simplifying that to indicate what your graph would be, what the ends of your graph would be similar to. So this is, again, not what the graph itself looks like, but what the ends are going to be doing. Now, number 16, there's really no simplifying here. So my end behavior model would be just the same thing as x to the 4th. If we think of this graph, what does an x to the 4th graph look like? Yeah, it's like a stretched out parabola, right? You might have some craziness happening here, but since my leading coefficient is positive, that means that my ends are going to be going toward positive infinity. So this one you could just think of your graph, and as x approaches positive infinity, my end behavior is approaching positive infinity. So we would have that DNE positive infinity. Now, that's considering the end behavior model, which here was pretty much the same as just the graph itself. The other thing you could do is say, okay, we're approaching positive infinity, so let me take a really large positive number. If I put in 1,000,000, or if you would, if I plug in positive infinity, but again, bear in mind it's not an actual number, so you can't really plug in an actual number. But if I plug in positive infinity, am I going to get back positive infinity or negative infinity? Yeah, positive infinity. Positive, really large numbers that's positive to the fourth power just going to be another really large number. So those are kind of your two options. Consider end behavior or just plug in a really large positive number or plug in positive infinity. So for number 17, again, we can think of our graph. The end behavior on the left-hand side is still going to be approaching positive infinity, so D would be positive infinity. Or again, if we plug in fake negative infinity to the fourth power gives me what? A positive infinity, because it's that even power, so again, it's going to be heading to that positive. Now notice the difference when we go to numbers 8 to 19. If we think of the graph 2x cubed, that's going to be similar to just the graph x cubed. We know our end behavior of that. So as x approaches positive infinity, we can see from our graph it's going to be approaching positive infinity. And as x approaches negative infinity of our graph, we can see that approaches negative infinity. Now again, what you can do is just plug in positive infinity. Positive infinity cubed is going to still be positive, but negative infinity cubed is going to be a negative overall. So again, you can go either way with that graph. All right, go ahead and give number 20 a try. Then we'll do 20. What's our conclusion for number 20? A infinity. So again, my end behavior model would be that it mimics the 2x cubed graph. We know what that looks like. Or if you just take a negative infinity and substitute it in, then we're going to end up having negative infinity cubed gives me back again negative infinity. So we have the largest term is going to be approaching infinity. Again, that largest term is what takes over the graph. That's what determines what happens. All right, so 21. This is where behavior gets a little more helpful. All right, so again, I can take positive infinity and consider the leading term on top, the leading term on the bottom, or the largest term on top and bottom. If I take my terms on top and bottom and consider what that graph looks like, my end behavior model is that it's going to mimic x cubed over 3x squared. Which, would you guys agree that that's just going to be the graph 1/3 x? If we were to simplify that down, we'd get x over 3 or 1/3 x. So my end behavior model is 1/3 x. Well, we know what that graph looks like. As I approach positive infinity, what is my graph 1/3 x approach? Positive infinity. So my answer is going to be DNE positive infinity. Or again, you can take positive infinity and substitute in. We get a positive on top, positive in the denominator, so overall positive. So similar with number 22. Again, let's take a look at my end, or my largest terms. So my end behavior model would be, if I simplify this down, I'd have negative 4x squared, negative 4/3 x squared. Well, we know what that graph looks like. That's going to be a parabola, but flipped upside down, right? So as x approaches positive infinity, where's my graph headed at that? Negative infinity. So D and E, negative infinity. Or again, if you plug in positive infinity, on top, positive infinity to the 7th is going to be positive infinity, but we have a negative times that, so we get a negative on top. And in the denominator, we have positive 3 times the positive infinity, so positive denominator, so overall negative. Okay, so the end behavior model usually helps take care of any issues you might have when plugging in negative infinity, because that's usually where most issues come from. So for example, with number 23, again, take a look at your largest term on top, largest term of the denominator, by end behavior model. So the ends are going to act in the same way as my graph. Let's see, this would become 2/3 and x, so 2/3 x. And again, we know what that graph looks like. So as x approaches negative infinity, my limit would be also negative infinity. Or again, if you substitute in a negative value, so we end up having -2, so negative times. Negative infinity cubed is going to be a negative. And then -3 times negative infinity squared would be positive. And that would give me positive on top, negative in the bottom, so overall negative. So whichever method you prefer is perfectly fine, whether you want to plug in positive or negative infinity or do the end behavior model, it will result in the same answer. You're basically doing the same idea, it's just the end behavior model allows you to think of a graph you're more familiar with and think of those ends. Plugging in just means you have to deal with some negatives and figure out what it is. Questions on that section? Okay. So now we've got the fun kind with 2 horizontal asymptotes. All right, so with 2 horizontal asymptotes, we have to think back to, I think Algebra 2 is one, most of you probably learned this. The square root of x squared, what does that equal? Plus or minus x, right? We also define this as the absolute value of x. So this is key here. The square root of x squared, or any even power, is the absolute value of that x. Now, in terms of solving, we would just say plus or minus, right? But the absolute value kind of takes care of that issue. So when we have these types of graphs, you can see it's no longer just a rational function, but rather a polynomial and radical. This is often where we have those 2 horizontal asymptotes. So what you have to be careful with here is whether we're dealing with positive infinity or negative infinity. And whenever we simplify that radical, we need to consider the absolute value of it. So again, that's anytime we have the radical of an even power to the absolute value of it. So let's take a look at what that looks like. So for number 24 here, again, we're going to take a look at our largest term on top and our largest term in the denominator. So again, with that top, the 3x is going to take control of the numerator. And our denominator, that 4x squared, underneath my radical is going to take control. This -2 and that +1 become insignificant when we're putting in really large numbers. Now, this is not 4x squared, but the square root of 4x squared. So our end behavior model with this, we have the 3x on top, but in my denominator, it's the absolute value of 4x, right? Or sorry, 2x, oh my goodness, the square root of 4 is 2. Let's fix that. Absolute value is 2. Okay, so the square root of 4 is 2, the square root of x squared is absolute value of x. Now we can take that 2 and put it out front, right? We know the absolute value of 2 is just 2. That's fine. I'm just leaving it in because it's easier. So now when we take our infinity and substitute it in, if we look, what type of, aside from the absolute value, what type of equation do we have here? Top heavy, balance, or bottom heavy? Balance. So we would expect it to be the 3 halves. Now this is, so we're going to treat it like normal using those 3 cases. The only thing that changes is if we're substituting a positive or negative infinity, that can impact whether it's going to be positive 3 halves or negative 3 halves. So it's really, it follows the same cases as before. You just have to consider, is that giving me the same horizontal asymptote with the negative version. But here if we look, we put in positive infinity, we're still going to have a positive overall, so we're good. Our answer is just simply that 3 halves. Now our issue comes into play for one like 25. So you can see it's that same problem. but now we're investigating negative infinity. Alright, so again, when we look here, that end behavior model, what's happening is we have the 3x over the absolute value of 2x. So again, we can expect that our horizontal asymptote is going to be 3/2, but is it going to be positive 3/2 or negative 3/2? Again, we have that balance, so we just take the coefficients, but when we look, this is negative infinity. So if I take negative infinity and put it in, what do we get up top, positive or negative? Negative. And if I take negative infinity and put it in the bottom, what do I get, positive or negative? Positive. So that ends up giving me an overall negative, so that means we have a horizontal asymptote of negative 3x. So this function, that 3x minus 2 over root 4x squared plus 1, the ends have two different horizontal asymptotes. On the right-hand side, who knows what's going on in the middle, but on the right-hand side, it's headed to positive 3/2, and then on the left-hand side, it's headed to negative 3/2. Some craziness is happening here, I don't know. But we know that the ends have two horizontal asymptotes. Okay. So same scenario as before. It's just when we check if it's top heavy balance or bottom heavy, we have to consider we head into negative or positive version of that horizontal asymptote. Okay. Questions on that? So go ahead and give 26 and 27 a try.
You know, you would think that it's supposed to be because when I would give them something more exciting, but we're just going to stick with it.
Do you notice 26 and 27 are slightly different? 26 is x squared, 27 is x squared. It's good to do. Just don't you dare say this equals the absolute value of 4x over 4x. That is huge. The limit does not equal a function. Alright, so 26, square root of 16x is 16x squared would be the absolute value of 4x. And down here we have 4x squared. What type of scenario do we have here? Top of the bounce off. Okay, so that one, plain old 0.
So would that not matter if it was positive or negative?
Yeah, it wouldn't matter because the bottom heavy is just 0. Now, when we have that balance, that's where we have an actual coefficient, like positive 0, negative 0, it's still just 0. But positive of a number would be different. Alright, so 27 though, it actually gets a little more exciting, I think. Absolute value of 4x squared over 4x squared. So when we take our coefficients there, its balanced coefficients will give us 1, right? But we've got to consider we're going to negative infinity. So if I take negative infinity and put it in the top, I get positive. But if I take negative infinity and put it in the bottom, what do I get? Positive. So it's still just a positive 1. So don't let the fact that you're headed toward a negative infinity make you think it has to be a negative asymptote. Not necessarily the case. I think this one ends up being the same asymptote on both sides. Alright, so then 28, again, we're going to have for end behavior model. We've got 3x over absolute value of square root of 2x. So positive infinity. That's going to give us positive on top, positive bottom, so we're good. 3 over root 2, which when we rationalize, 3 root 2 over 2. Good with that one? And then 29, again, similar, my end behavior model. So on top, I've got the 3x, and that denominator, absolute value squared of 2x. Again, those match. This time, though, when I take my negative and put it in, I get a negative on top and a positive at the bottom. So I'm going to get that overall negative 3 root 2. Okay. So again, be mindful of the fact that you might have those two horizontal exponents. It's basically when you see that radical thrown in there. And don't automatically assume negative infinity indicates negative horizontal exponent. Questions on those? They're not that much. Okay. And then type 5 here, we're dealing with trig. So again, you can think of just taking a value and substituting it in. You might have to do some trig substitution, but we can go from there. All right. What is the limit as x approaches infinity of sine of x? What's happening at the far right-hand side of the sine x graph? Show me with your finger, your arms, what's happening. Yeah, it's just oscillating back and forth, right? And remember, it needs to approach a single value, it needs to narrow down to a single value for it to exist. So if it's just oscillating back and forth, what's my answer going to be? Just a plain old D and E. Nothing fancy with it. Alright, now 31, we know the limit if x was approaching 0. But here it says x approaches infinity. So we've got to use our noggin for this. Again, let's think of our numerator. What is the largest that our numerator could ever be? 1. And again, the smallest it could ever be is -1. So it's limited between those two values. It's not going to be increasing toward infinity or decreasing for negative infinity. But what about my denominator? What's happening there? That's just super duper increasing. So if I think about this overall, my denominator is going to be rapidly increasing and taking over the whole thing. So again, if I have a small number over a really large number, what is that overall limit headed toward? 0. All right, now 32. If I take a really large number and substitute it in, 1 over a really large number is basically 0. And what's cosine of 0? 1. So as we put in larger and larger numbers, this value is getting closer and closer and closer. So 1 over a really large number, if we plug in infinity, 1 over a really large number is practically 0. Cosine of 0 is 1. So as this gets closer to 0 by limit, the cosine of almost 0 is 1. All right, 33. All right, we've got a couple options. We could do a double angle identity in there, right? But let's maybe break it up using our properties. Let's go ahead and change this to the limit as x approaches infinity of x over 2x minus sine 2x over 2x. Okay. Now, if we take, again, the properties and apply it to that first one, what's going to be my limit as x approaches infinity of this first chunk here? 1/2. Okay. Now we've got to think about this next chunk. As x approaches infinity of this chunk here. All right, again, if I have infinity going into sine 2x, again, sine 2x, what is the largest value that that graph can take on? Still 1, yeah. What does the 2 actually impact on my sine graph? The period, the period or the frequency, yeah. So it affects your period. It affects how quickly it bounces back and forth. It does not affect how high or low it bounces back and forth. You think that it's a horizontal stretch, not a vertical one. So again, even if I put it in infinity or a really large number, the largest it could be is +1, the smallest could be is -1. So again, what's taking priority in this fraction here? The bottom. The bottom's going to grow tremendously. The top's going to be some single number. So what is this whole thing going to be? What's going to be the limit of this whole thing here? 0. So we have 1/2 minus 0, which is 1/2. So just like when we saw trig sneak into some of our earlier problems, you really just had to kind of reason through it and use what you know about these. Questions with any of that? So we're just going to dip our feet into the water of continuity before we get started. You guys have that. Alright, is there anyone that did not get the notes? Okay. So again, continuity I know is something that you dealt with probably last, or well, you've dealt with it actually. I think in Algebra 2 was your first time dealing with it. So we're just going to briefly talk about it before the class ends here. Now, in Algebra 2, how did they tell you to determine if a function was continuous? Yes, but what did they tell you with your pencil? Trace it, and if you had to pick it up, and that meant it wasn't continuous there, right? So that's our nice and easy Algebra 2 definition. But the actual definition, you can see here, and you've probably seen this, is that your left hand and right hand limit must exist. They must equal each other, which means the overall limit has to exist. And the function value has to be defined at the point of question. And whatever that value is must equal the overall limit. Okay. Now, what are the different types of discontinuities? I heard some of you guys say it earlier. I heard holes. What else did we have? Jump, and what's their last one? Yeah, what does an infinite discontinuity look like? Yeah, some type of vertical aspect. So next class we'll be delving into those different scenarios, kind of taking a look more in depth at what continuity means, what that means for us in terms of graphs as well as algebraically. And also, we'll take a look at piecewise functions and things like that. But the key thing here, and we'll make a little note on this, is that it looks very similar to our limits, right? Our limit said that in order for this to exist, we had to have the left hand and the right hand had to be equal. Well, the new piece now, building upon that for continuity, is that our function value has to exist and that it has to equal your limit. So on that first day of notes, it started asking us what was f of 2, what was f of 5. It didn't make an impact for our limits, but it makes a difference for our continuity. So really, our continuity can be kind of just summed up in this very last statement here. F of c equals the limit as x approaches c of f of x. The reason why it can be summed up here is if f of c equals whatever limit that value is, that means that f of c exists. And if my limit equals whatever that f of c value is, it means my limit exists, which means that the left hand and the right hand are the same. So we have kind of the first two are kind of described. The core calc on the AP exam, when they ask you to justify, you do have to specify all three things. And if it fails, you have to specify the third things. So here on the front are just kind of those three cases of which it's a fail. So our first condition is that it's not defined. If it's not defined at that point, then we can't even have the continuity at all. That's immediately going to be a hole or could even be a hole. If it fails condition 2, meaning that the left hand and the right hand limits are equal, so the overall limit does not exist, then it can't be continuous. So here we have that the function is defined. We have a left hand and we have a right hand, but they are not equal, so thus the limit does not exist, which means that it's not continuous at that point. And then the failing condition 3 is where we have the function is defined, we have the left hand and the right hand are equal, so thus that overall limit exists, but these two values were not equal, so thus it overall. Okay, so if any of those three break down, right. So your homework is that homework that I passed out. Remember, we will have a quiz next class over limits. That's it. We'll continue next class with continuity. Yeah, just on limits. We won't have continuity on that case. Thank you.